Welcome to Read Along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is subsection 6.3.6, vertices, edges, and faces. So in this graph, we have vertices and we have edges. What are faces? We'll talk about what that means. Let's look at this. Let's analyze this graph a little bit. There's some one direction cycles, meaning like, okay, so we go E1, E4, then we go backwards on E2. We can express that with a negative sign here. That's a cycle. Here's another one, another one. Okay, so we have some one direction cycles. Okay, we can follow one cycle, then another, and we can still have another cycle, right? So we can kind of just have cycle after cycle. In fact, what we can do is we can think of taking all cycles like that as even a subspace. And in that subspace, what's the dimension of that subspace? What's the minimum number of cycles that you need in order to span to create that whole subspace? It turns out in this particular case, the small that has dimension 2, and we can call that dimension, or kind of the number of basic cycles that all the other ones are made up of. We can call those faces if we like. In this particular case, let's look at this again. So we could have this is like a basic cycle, and this is like another basic cycle right here. We can call those faces. Now, we can also think of it as basically like regions. See how this graph kind of splits the plane up into parts? Here's a part here, here's a part here, and then on the outside, there's another part. So we'll call them like faces. In fact, if we wanted to, like think of putting this on a ball, right? Like this graph on a ball. And then if you made this part of the ball like rigid, like flat, and then this part like flat, and then maybe have this other one like, curved, that's fine. But you can literally kind of think of each of these as being like a part of the surface, like a face of the surface. So there's like 3 faces here. Okay, so 2 of these regions correspond to the basic cycles, and then the outside region is like, it can be considered a face as well. Okay, so the dimension of C, so what is C again? Let's review. Up here, C is like the span of all the cycles. The dimension of C is just 1 less than the number of faces. All right. Okay, and that's kind of how because number of faces was 3, and the cycles had dimension 2. Okay. What is a planar graph? A planar graph, okay, all right, is a graph where there's a way of drawing it so that actually we can put all the faces like on a ball or on the plane, if you will. If you have a face out here and then you have individual faces here, but you don't have faces overlapping or going on top of other faces. You can actually draw it in some way. So if there exists some way of drawing a graph, there could be ways of not drawing it that way, but isomorphically, if you can change your picture so that you can actually visualize the graph this way with different faces occurring in different parts, that's called a planar graph because it can occur on the plane. You can kind of look at it nicely on the plane. Okay, planar graph is a graph in which a collection of basic cycles which minimally generates C's and projective corresponds to the regions the graph splits the plane into. Okay. Okay. So, and in this particular case, when that occurs, then the number of faces minus 1 will be the dimension of C in that particular case, if we can do that, if it can be a planar graph. All right. So, for instance, take a look at this graph right here. This is actually a planar graph, even though it's not drawn as a planar graph, because we have like this region is overlapping other regions. But if we redraw it like this, So it's an isomorphic redrawing, has the same structure, just drew it differently. It looks very planar here. You have your different regions. So something interesting to think about is this idea, like from the Smith normal form of the incidence matrix, the dimension of the range plus the dimension of the kernel is equal to the number of columns. That's true for any matrix, especially we had an analysis of the Smith normal form to get there. So remember what the dimension of the range was earlier. It was 1 less than the number of vertices. Okay, hold on. Yes, so that's true. And the reason why it's 1 less than the number of vertices is because to get the dimension of the range, you're getting getting the dimension of what you're modding out by when you're looking for connected components. And in doing so, it's kind of like creating a tree or creating a forest. And if it's connected, it's going to be a tree. And so the dimension that you get is actually equal to the number of edges there, which is 1 less than the number of vertices. So you can adequately say that the dimension of the range here is actually 1 less than the number of vertices for the incidence matrix. The dimension of the kernel, this is interesting, is the number of basic cycles. So the cycles are what in the Smith normal form, are what in the incidence matrix actually, go to or create columns of zeros when we go to the Smith when we go to the Smith normal form, because each cycle is kind of like a relation that you can use to make a column 0. So so the number of 0 columns actually ends up being the dimension of the subspace of cycles themselves, or the number of basic cycles is the dimension of the kernel. And remember that this is 1 less than the number of faces. Number of columns, remember that's the number of edges. Okay, the total number of edges in general. So actually we can rearrange this idea as follows. So this is assuming we have a planar graph, so that actually because in a planar graph, remember that this dimension right here of the basic of the cycles is 1 less than the number of faces. That happens for a planar graph. So using that idea for a planar graph, we can, if we use some notation, number of faces, number of edges, number of vertices, we see this is the dimension of the kernel, 1 less than the number of faces. Dimension of the range is 1 less than the number of vertices, because it's the number of edges as we get that Smith normal form in there of looking at the incidence matrix. And that's going to be the domain, which is the number of edges. We rearrange this and we get a 2 on this side. We have a negative number of edges here. So number of faces minus number of edges plus number of vertices is equal to 2. And that's always true for a planar graph. So if this fit condition fails, then you know it's not planar. So if it is planar, this works. And if this doesn't work, then it's not planar. Notice we haven't said anything else. Those are the only 2 statements we've said. Doesn't cover all cases. That just covers the case if it's planar, it's true, and if it's not true, then it's not planar. So supposedly, then perhaps it could potentially be true and yet not be planar. So basically, it's a way of showing showing that something is not planar is really what it is, because if something doesn't satisfy that, then it won't be planar. That's kind of the idea that we have. Here's just a thought example. So an example just for some thoughts. There's 5 vertices and the number of edges. Well, there's precisely 1 edge between every pair of vertices. So among 5 vertices, 5 choose 2. There's 10 edges, or you could count them. So we have So what would the number of faces be if this happened to be planar? There would be 7 faces if it were planar. So try as you might, you're gonna, if you were able to draw it as a planar graph, then there would be 7 faces in there. Um, Intuitively, you can kind of think, well, maybe a cycle happens for every um, pairing of 3 vertices here, right? So 5 choose 3. That's already more than the number of faces there, which would make this equality fail and therefore be not planar. Of course, this was kind of a guess. That would be, is that really like, how many there are? Different basic cycles. Of course, then you'd have to add 1 for the total number of faces. So, you can kind of think of it that way. But in the exercises of this section, we actually walk through a specific way of how we can tackle this problem and actually show that it's not planar. So that's just looking forward to the exercises to figure that out. Thanks for watching.